All right, well, good afternoon. So this is a re-record of the lecture that I had yesterday for part one. Um, for some reason, it didn't, I guess it messed up as soon as I started showing the video. So hopefully everything works better today. Where we ended up at the previous lecture was talking about molecular shapes. And again, these are the only 5 that you will be responsible for. There are something like 13 or more different types of geometries, but I'm not going to ask any questions related to those. And so these are some typical shapes, and you should know the angles involved. And so, for instance, if it's linear, that means that this angle is 180 degrees, and this, for instance, is carbon dioxide. And so on an exam, when I am asking for the shape or geometry of a molecule, what that means is that you first have to draw its Lewis structure and then use this valence shell electron pair repulsion theory, okay, to figure out which one of these, in your case, which one of these 5 geometries it will be. Okay, and the shape, as we talked about last day, is really governed by how many electron pairs you have around this atom, the central atom. Okay, so if we look at the Lewis structure, you'll see that, the oxygens also have lone pairs, but for shape purposes, we really could care less. Okay, so this is the proper Lewis structure. But shape is really only governed by lone pairs here. And the effect that it has is lone pairs take up space. And so if you have a lone pair on the central atom, then you start to repel these electrons in the bond. Okay? And so that causes it to have a bent geometry. Okay? And so here, if you look at the effect of this, you go from 180 degrees with no electrons on the central atom. If I put 1 electron pair, like we have for ozone, now that goes from 180 to 117. If I have 2 electron pairs, I guess it's not shown here, but you have 2 electron pairs here. Now the angle's even smaller, 104.5. Okay, so it's important to realize that as you increase the number of electron pairs on the central atom, then you get repulsion between the bonding electrons and the lone pair. Okay, and that means that the angle will decrease. Okay, the angle between the atoms, I guess. Okay. All right, so what we're going to talk about here, the context, so this first part of the lecture is related to the context of climate change. And so we're really just concerned about what happens to a molecule when infrared radiation is absorbed. And infrared is not strong enough to break bonds like UV is. And so the only thing that'll happen is, if you think of bonds as little springs, you can either stretch or bend these springs. Okay, so we call those molecular vibrations. And then microwave is even lower energy, so you can't even bend or stretch these bonds, but it just kind of rotates the whole molecule. Okay, so again, we are going to talk about molecular vibrations. And so how do you know if a certain molecule will absorb infrared radiation or not? And so IR radiation is absorbed if it causes a change in the charge distribution. of the molecule. Okay, and what I mean by charge distribution is if we look at carbon dioxide, okay, and we draw its Lewis structure, okay, remember that we talked about electronegativity? Okay, that means, you know, how easily an atom pulls electrons toward itself. Okay, and so remember, you know, if we looked at the periodic table, like that, we saw something way down here has a very low electronegativity, and it increased as you go up a group or across a period. Over to fluorine was the highest electronegativity. Okay, and so oxygen is farther to the right than carbon, so these will have an increased electronegativity. And so we can write that as little delta negatives here. And that's really saying that this side of the molecule is pulling electrons away. Okay, you can write it as little dipoles too, saying that electrons are moving away from this central carbon atom. Okay, and so the ends of the molecule become negative, and the center becomes positive. Okay, and so when you are absorbing radiation, infrared radiation, only the vibrations or bending that will change these charge distributions will correspond to absorption of that infrared radiation. Okay, and so if you consider CO2, there are different ways that this molecule can stretch. Okay, so A and B correspond to stretching frequencies. Okay, and so yesterday I put the camera on. Let's see, I think I've got a camera on here just to show this a little clearer. Yeah, photo booth, I guess. I think that will work. Okay. Hello. I think this is just a photo of it, but at least I think you can see it, hopefully, if it's recording the screen. Okay, so if we look at A here, okay, so A's stretching, you can think of that as these are the oxygen atoms, and then I guess my head is the carbon atom, and this is called a symmetric stretch, where they're going out and in at the same rate, okay? And so this will not change the charge distribution of the molecule, right? So you're still going to have the negative ends there and the positive in the middle, okay? And so as a result, this symmetric stretching will not result in absorbing infrared radiation, okay? But this anti-symmetric stretching, where you've got, for instance, one is going away as one is going in, so sort of like this, okay? That is changing the charge distribution of the molecule, right? Because now, if one is away, now you've got this negative charge way out here, and this negative is now pretty close to the center, like my head, the carbon atom, okay? So now the charge distribution is very different than this scenario, right? Okay, so symmetric stretching, it's always equivalent. This one, not so much, or that, okay? And so this stretch will correspond to infrared absorption, okay, as well as bending. Okay, so if we do this, okay, or like kind of scissoring or whatever like that, those will all correspond to infrared absorption, okay? So in these different possibilities, this one, anti-symmetric stretch, and these different types of bends, these will correspond to infrared absorption. And so if we do what's called an infrared spectrum, okay, where we put carbon dioxide and then we hit it with infrared radiation and then use a detector to see, what's being absorbed, this is what it looks like. Okay, so this is your background. Okay, and then, so this is no absorption of infrared, and then it'll go down, which means you have a peak, and this means that IR is being absorbed. Okay, so like 0% is being transmitted. Infrared is being transmitted through CO2. It's all being absorbed. And this corresponds to stretching. Okay, and then we've got C and D, those different types of bends, are down at this end. And it's a little broader because you have really two types of bends, right? You've got this one and that one. Okay, and so what's important to look at on this spectrum is that, remember, as you decrease wavelength, then energy increases. Okay, and notice that over here, so as you go this way, you are decreasing the wavelength, right? It's 4 micrometers or micrometers here, and then it's like 10, 15, 20 down here. And so as you decrease the wavelength, that means the energy is going up. And so what that means is that it takes more energy to stretch bonds than to bend them. Okay? So this is down at the higher wavelength or low energy region. So that means bending is easier to do on a molecule than it is to stretch. And that kind of makes sense if you think about these as springs, right? It takes more energy. You think of this as a really stiff spring. It's kind of a workout, right, to pull these apart, versus this, to bend it, you can just kind of, push a little bit, maybe in this one. Okay, just push it up a little bit and you've already bent it. Okay, so it doesn't take as much energy. All right. Water is also, so if you look at the spectrum then, in other words, since this spectrum is showing some peaks when you introduce IR radiation, that means it is a greenhouse gas. Okay, it will absorb IR radiation. And water will also do that. It's a little more complicated, but you've got bending here and then stretching here. Okay. And so this water is also a greenhouse gas, okay, just like CO2. Okay, and so I'm just going to, you've already read the chapter, as part of your reading assignment, so you've already seen this, but I just want to go through it with you. So one way that people have, so scientists have found out about carbon dioxide concentrations from years ago, and this is, going back hundreds of thousands of years even. You can get concentrations of CO2 by these trapped air bubbles in ice. And so they'll take these ice cores, and then you've got all these trapped gases, and they will sample that gas. And it's really interesting that they can get greenhouse gas concentrations over time from this. And so this is, back in the day, this is only goes back to 1750, but they can go back and get ice core data from a long time ago. And so, that's kind of, we're using ice core to find out kind of historical concentrations. And then now we can actually do atmospheric measurements. So we can actually find out, just by sampling the air, how much CO2 there is in it. And what you'll notice is that it is going up dramatically. Okay, it's kind of like, the trends you see in COVID-19 right now, it's going up like that. Okay, so pretty dramatic. Very different time scale, because we're looking at like COVID-19 is going up like this on like an hourly or daily basis. This is over years, so it's, it's slower, but it is going up dramatically over time. But CO2 is not the only greenhouse gas. So we've got methane that's also going up pretty dramatic, and a lot of these NO gases, so nitrous oxide too, is going up. Okay. And so this really is, this and the next slide is really the smoking gun evidence of climate change, that it's really due to CO2 concentrations. And if you look at from ice core data way back in time, you can see that there's a fluctuation always with CO2 concentrations. And so there's a video called The Great Global Warming Swindle. And it's a BBC production. You can find it probably on the web pretty easily. If you, in your classrooms in the future, if you want to show it, I've done this in the past, where we're kind of face-to-face and we can have, debates in class. I'll show the class this video and then an inconvenient truth, for instance, back to back, and then have people debate, choose sides and have a really healthy debate about these issues. And what this global warming swindle video showed, as well as a lot of websites or videos or whatever, blogs, what they will do is kind of cherry pick the data. And so that video, they didn't show any CO2 concentrations higher than where my cursor is right now. So right here. Okay, and so if they're not showing anything higher than that, like in more recent years, in other words, then their conclusion was that, yeah, CO2 is high, but it's not any higher than it was back here, 350,000 years ago, and everything was fine, right? So it's just a natural cycle. But if you go to show what concentrations are now, you'll see that we are higher with CO2 than we have ever been the last million years. Okay, so that is not an accurate statement that people are claiming. And then, so the who cares of so CO2's higher. This is the other evidence showing that CO2 concentrations, blue, and average temperature on Earth, red, follow one another pretty closely. So I'd say there's a very strong correlation between temperature and CO2 concentrations. And so, we'll have to see, as we have more recent years, is this red going to continue to climb up here? But all indications that it will. Okay, so it followed even these fluctuations. The temperature followed it. Okay, and so I think this is a really good piece of data to show that temperature and CO2 concentrations are correlated. Okay, and so this is what we know, that CO2 contributes to global temperature. And it's being elevated in recent years, that the concentration of CO2 has been increasing over the past century, and it is a consequence of human activity. Okay, so if it's going up, there's no other reason why it would be going up other than us putting it there, right? So it's not a natural cycle of anything. Okay, people talk about natural cycles of maybe sunspots or sun activity is corresponding to this global temperature increase, and maybe there is a part of that that can explain it, but human production of CO2 is also a very strong indicator or a driver of global temperatures, okay? And so this is what might be true. So CO2 and other gases, okay, so we're talking like methane and NOx gases that are all generated by human activity, they are responsible for the temperature increase. So this is very likely the case, and that it's also likely that the global temperature will continue to rise as we start pumping those gases in the atmosphere. Climate modeling can get really complicated, and so they've got these forcings, and the more positive the forcing is, the more it's going to increase global temperatures. And so things like CO2 has a huge positive influence on temperature, and same with methane, other gases. Whereas things like aerosols or dust in the air, cloud cover, that will have a negative forcing, okay? And so in all the climate models, they're putting all these in. So particulate matter, if it's present, that will have a negative influence. That'll have a cooling effect on Earth's temperature, okay? And so then they put it into these models, And the black curves here, I don't know if I can blow this up so you can see it. So these are different continents on Earth, and you can see the black is the actual data for average temperature in that part of the world. And then they looked at, modeling it based on natural cycles. So sun activity, for instance, that's the green. And then they brought in based on carbon dioxide concentration. So man-made activity, anthropogenic, and you'll see that the pink, which takes into account human activities, it matches almost exactly in any part of the world, a lot more closely than if you just considered natural causes. Okay, and so quantum, global averages here is this. So again, human activity, corresponds very closely versus the green is nowhere close. Okay. So again, some very strong evidence there. There's this Intergovernmental Panel, or IPCC, on climate change. And their latest report, I think, is 2018, actually, but they all agree that, human influence on climate is clear, and they give grave warnings, really, if we don't do something about it. The real question is, what could we do at this stage? I think it's almost too late to do anything, to be honest. I mean, people are saying electric cars are the cure-all, but I don't think so, because during their use, they don't produce CO2, but how much CO2 went into building these cars and the battery packs and everything? And so I don't think it's really a net gain as far as, producing less CO2. So as population grows, I think it's just one of these things that we're just going to have to deal with and start coming up with plans to offset its effects at this point. I don't think we can ever go back anymore, but it's just going to be a reality that we're going to have these really severe climate consequences of, more flooding. So, places like New Orleans is going to be flooded more frequently, and it could even be wiped out in our lifetime. And it's just due to all of this occurring. Okay, so our future is really up in the air. We're losing more ice cap. Okay, and this is a natural cycle too. So people that don't believe in climate change per se, they'll say, well, yeah, it'll go away and then come back in the winter months. But if you look at kind of that increase and decrease cycles, we'll see that in recent years, this is what it used to be. And now we're talking, this is the current ice pack, and then that's when it kind of comes back. So it's a lot less mass than it used to be, okay? And so then you start to affect even marine habitats, okay, by, as you are melting more ice, then the pH and concentration of salts in oceans decreases, the temperature increases of the saltwater oceans, and so it could have huge effects on just ocean life as well. So we really don't even understand the whole range of implications for this yet, really. And so legislation, so really the only one that everybody kind of came together on was a long time ago. So the Kyoto Protocol was in '97, and so that established goals to stabilize, reduce these greenhouse gases, and the ones they focused on were these ones. Okay, so CO2, but also nitrogen monoxide and these other HFCs that are CFC replacements, from the previous chapter. And then they allowed trading of emission credits. And so this is kind of a complex topic, cap and trade, and you'll hear carbon tax mentioned in Canada. And so I thought I would put a video to just bring clarity to those concepts. And so here is just a short video just to talk about what governments are doing, not so much in the US, to be honest, with our current president especially, but in Canada, they're really talking about carbon tax and then a cap and trade system for industries.
Greenhouse gas emissions come from the goods and services we produce and consume. The market for goods and services fails to account for these emissions, and they have impacts that are not priced as a production cost. This represents a market failure. Economists around the world tell us that the simplest and least expensive way to correct the market failure and reduce the amount of carbon dioxide being dumped into the atmosphere is to put a price on carbon emissions. Increasingly, governments are introducing carbon levies that improve market efficiency by allocating the costs of impacts to their emission sources. Evidence shows that carbon pricing reduces emissions, stimulates innovation, and raises revenues that can be recycled back into the economy. Let's take a look at the two major approaches to price carbon. The first is imposition of a carbon tax on fossil fuel consumption. This puts a direct cost on carbon emissions produced when a fuel is burned, such as gasoline, diesel, natural gas, or coal. Greenhouse gas emissions resulting from non-combustion processes, such as the venting of carbon dioxide extracted during the processing of raw natural gas, can also be taxed in this way. Direct carbon taxes offer three key benefits. Emissions decline because consumers reduce their fuel consumption when costs go up. Producers become more efficient by adopting higher efficiency technologies and cutting waste. And carbon tax revenue can be used to fund environmentally beneficial projects, reduce income or employment taxes, and help society adapt to climate change. Carbon taxation is not new. Finland launched the world's first carbon tax in 1990, covering energy content of fuels and carbon dioxide emissions. Sweden adopted Finland's system a year later. Great Britain introduced a carbon tax in 2001 to reduce energy usage, with revenues targeted for energy efficiency improvements and renewable energy support. Australia set up a carbon tax in 2012, pricing carbon at 23 Australian dollars per tonne of carbon dioxide emitted. The Australian scheme targets the 300 largest emitters, and the price will increase each year until 2015, when the country will shift to a cap-and-trade system. The revenues generated from the tax will be used to reduce net income tax, increase pensions, and social welfare payments. In Canada, the province of Quebec led North America by applying a small carbon tax in 2007 on petroleum, natural gas, and coal. Today, the tax raises $200 million per year for climate change initiatives in the province. In 2008, British Columbia followed suit with a more aggressive carbon tax of $10 per tonne of carbon dioxide emitted. In an important innovation, the tax was set to increase by $5 per year through 2012. It now sits at $30 per tonne per year. This adds 7 cents to the cost of a litre of gasoline in British Columbia. By scheduling the annual increases as much as 5 years in advance, consumers were sent a progressive signal that encouraged less fossil fuel use. British Columbia's carbon tax covers about 3/4 of the province's total emissions. These are generated mainly from fossil fuel combustion and include natural gas flaring. The remaining untaxed emissions largely result from industrial processes in the natural gas, smelting, and cement industries that do not involve combustion of fossil fuels. What are some of the benefits? By law, all revenues from the carbon tax are used to reduce personal and corporate income taxes in the province. British Columbia now enjoys the lowest personal income tax in Canada for net incomes up to $119,000 per year, and BC's corporate income tax rate is among the lowest in the G8 countries. Moreover, British Columbia's carbon tax is working. Since the tax was introduced in 2008, fossil fuel consumption has declined more rapidly in BC than in any other Canadian province. And over the same period, BC's gross domestic product grew faster than the Canadian average, suggesting minimal impact on the province's economy. But BC's carbon tax will need to rise above $30 per ton to encourage further reductions in fossil fuel use. To be consistent.
And so just to bring an update to this, the current carbon tax in BC is higher than $30 per ton. It's actually 45 now, and it'll go to a cap of 50 in 2021. And so, there's a lot of complaints from British Columbians of how expensive their gas is, just due to this tax.
And fair, the tax could be applied more broadly to cover non-combustion process emissions. Such changes will be easier to put into action when more regions of North America join British Columbia in pricing carbon. Now let's consider another approach to carbon pricing, cap and trade. It is different from carbon taxation as it targets industrial emitters and sometimes fuel suppliers. Governments require factories, power plants, and other companies to hold a permit, usually called an allowance, for each ton of greenhouse gas emitted. The total number of allowances available is capped, and over time it is reduced. Establishment of a trading market allows any company that exceeds its greenhouse gas reduction targets to sell or trade spare allowances to other companies that require more. In many jurisdictions, the price of allowances is set by auction. Thus, market rules of supply and demand establish a price for emissions, and that price will rise as the total number of allowances is reduced. Companies that are highly efficient in reducing emissions will reap the benefits of selling allowances, but those that are less efficient will pay more to emit. Cap and trade, like carbon taxation, is not new. Let's consider some international examples. The European Union Emissions Trading System is a good example of cap and trade system that targets heavy emitters. Although the European system has been criticized for granting too many allowances when it was first set up in 2005, it is expected to reduce emissions by almost 20% by 2020. Other jurisdictions are actively exploring the cap and trade approach. China, for example, now has 7 pilot cap and trade systems in operation at the provincial and city scales. In North America, California and Quebec established a joint cap and trade system that entered into effect in 2013. Like direct carbon taxation, cap and trade systems reduce emissions, encourage innovation, and raise government revenue, which can be used to support energy-efficient infrastructure, tax code adjustments, and adaptation to climate change. It has become clear in recent years that putting a price on carbon is the most effective and easiest way to reduce emissions. Such a price provides a direct incentive for society to move toward a low-carbon economy, and is catching on. By the end of 2013, it is expected that more than 30 countries and almost 20 subnational jurisdictions will have some form of carbon pricing in place. But while this trend is welcome, it is also insufficient. It still comes nowhere near to addressing the full external costs imposed on the planet by global warming. The need to appropriately price carbon thus remains a major challenge for humanity.
Okay, so I think the cap and trade system has a great potential for limiting how much CO2 is produced by companies. So, for instance, battery companies that are making these batteries for electric vehicles. I think, as it said, if you have these credits, it's to their benefit to come up with procedures, with processes during their fabrication that are going to be as good to the environment, efficient as possible. And so, so I think there have been a number of companies that, because of this in place, that they have totally revamped their whole processing plants to become more or I guess less CO2 emitting. Okay, and so I think that has a lot of potential. There's not a lot of talk recently though about it. So it was kind of back. Bush talked a little bit about it. Obama did more, and now it's just kind of in stalemate with President Trump. So we'll see what happens with it in the future. Carbon tax is something that you don't hear much in the U.S. either. In Canada, they're really trying to push it, and so Prime Minister Trudeau is really trying to push it down the throats, really, of the prairie provinces. So I'm from Saskatchewan, which is in the middle of Canada, and that's where the farming communities are. And so carbon tax would spell disaster for those farmers, and it really wouldn't do what it was intending to do, because a carbon tax is meant, so you're not going to burn as much fuel, so you're going to limit your fuel use. And so for us, maybe that would make sense. Okay, instead of driving today, I'm going to take my bike into work because I just don't want to pay more for gas. But for the farmers, they have a fixed amount of land. They have to plant it, and so they have to use the same amount of diesel fuel regardless of whether the tax is there or not. And so you're just it's viewed as unfairly taxing one part of the population or one industry. And so the farmers are going to have to dish it off on us with increasing price of vegetables and grains, etc. So food prices will go up. And so it's kind of this opens a can of worms that I don't know if it's really the right way to go with it, to be honest. And so I don't know. It's really, really controversial and something you hear daily almost. Before COVID-19, I guess, in Canada, all the disputes about this carbon tax. Okay, so that is the context of climate change. This is a website that I went through yesterday. This is the link. So, if you pause the video, you can type that in and go to this website. And what's nice about this website is that you can practice the stoichiometry calculations. And so part 2 of the video, we go into this one, okay, and do calculations. We're going to start here showing how to use this, this website to do these calculations. And so this is showing the unbalanced equations. And so let's say if we have 20 grams of sodium chloride, then let's do the calculation of how much silver nitrate we need to react with that, okay? And so this is, the types of questions that you'll have on your exam next week. Okay, this, and then you're going to form that and this. Okay, so the first thing you should do, okay, and so we have 20 grams of that, and we don't know. That's what we want to know, how many grams. Okay, and so for this type of calculation, the first thing we have to do is balance it. Okay, and so for this case, silvers, there's one on each side. So I think that looks good. And then sodium is 1, chlorine. Okay, so it is balanced as is, just with 1s in front of everything. Okay, so this is a really easy example. Okay, and so the calculation that you have to do is first calculate moles only for the substance for which you're given grams. Either moles or grams. So if you're given moles of it, then you are done already. But very typically you'll be given grams of something. So then you have to convert grams to moles. Okay? And then you just convert moles of substance 1, if you want, into moles of substance 2. Okay? In this case, substance 1 is going to be NaCl, and substance 2 is the silver nitrate. Okay. And then once you have moles of silver nitrate, then you calculate the grams for substance 2. Okay, so you go moles to grams. Okay, so that's your strategy always, okay, is look in the question, are you given grams of anything? If you are, then convert that to moles, and then convert it moles of something else, and then you can do grams. Okay, so let's do that. So step 1 then is we want to go 20 grams to moles. So you do 20 grams divided by the molar mass of sodium chloride. Okay, so sodium we'll say is 22.9 grams per mole, and chlorine is 35.45. Okay, so if we add those up, get my calculator here. So that's 22.99 and another 35.45. We get 58.44, and the units again are grams per mole. Okay, and so then grams will cancel, and you'll end up with 20 divided by that is 0.342 moles of sodium chloride. Okay, so that's step 1 is done. Okay, so now we have to convert moles of, I know I'm scribbling a lot here, but I want to go moles of this into moles of this one. Okay, and the question could have asked also, you know, how many grams of this are we producing? And then you'd have to do moles of this into moles of that. Okay, so it just depends what the question is wording or how it's worded. You'll get the important thing is that you can calculate moles of one thing, then you can get moles of anything else just based on these numbers. The numbers you put in when you balanced, okay? And so here it's a 1-to-1 relationship. Okay, so you will have the same number of moles then. Okay, so therefore, so step 2 then is, since NaCl to silver nitrate is 1-to-1, then you have 0.342 moles of silver nitrate. Okay, so the same number. Okay, if it were, you know, 1-to-2, let's say, so let's say there was a 2 here, then we'd have to multiply by 2, right? Because you're saying that there are 2 times the number of moles of silver nitrate. Okay, and on the flip side, if this were a 2, then you'd have to divide by it, right? Because you're saying that the silver nitrate only has half of what this does, right? This is twice the number on that case, so then you would divide. Okay, so you just have to look at those numbers and convert. And then now the last step is once you have this many moles, now you multiply by this molar mass. Okay, and so silver, I have to look up that one. So silver is 107.9. Okay, so silver nitrate, this is 109. What was it again? Whoops. It's 107.9. Nitrogen is 14, and then each oxygen is 16. So we'll just add those up here. So the molar mass, in other words. So we've got 107.9, 14, and then 16 times 3, because there are 3 oxygens. And we get 169.9 grams per mole. Okay, so now moles cancel, and we end up with grams. Okay, so times 0.342, and we get 58.1 grams needed to react. Okay, and so what this little website does is now we can add in silver nitrate. Okay, and so let's, if we just add a few grams, right? So let's add 5 grams of silver nitrate. You see that now we're starting to generate products. And notice what happens to sodium chloride as we add the other reactant, okay? It's going down, isn't it? So 16.6, 16.2, 15.9. Okay, so as we keep adding, the sodium chloride's going down. Okay, now we're at 5.9 grams, and notice the products are going up. Okay, but as we add this 58 grams of silver nitrate corresponding to our calculation, notice what happens. There's no sodium chloride left. Okay, and so this amount corresponds to just what we need to cause these products to be formed. Now, as soon as I start adding more silver nitrate, notice there is no change in product, right? So all that happens is we just have it left over in the flask, right? We have, this is going up as I keep adding more and more, and no more products are going up because we don't have any of this other reactant, okay? And so we would say in this case, with 84 grams of silver nitrate, and we had 20 grams of sodium chloride, that sodium chloride is the limiting reagent. Okay, it governed how much of the products we made, and this is excess. Okay, and so this semester we're not going to do really anything with limiting reagents. It's just that when you have grams of both reactants, if you're told, both of these, you would then have to figure out which one is in excess, and then you use the other one. But we're not going to do those calculations. So all the questions you're going to get this semester are like this, where you're only given grams of one of the components. Okay? And then that way you know that this is the limiting reagent. Okay, and the other one is going to be in excess. Okay, so you just use this and follow this 3-step procedure. Okay? All right, so that is the end of part 1. Part 2, we will move on to this question. Okay, so we'll work through that one together, and you can do that one. All right, and then I think we also go into this one as well, so just to give you more practice. Okay, so that is the video.